And now we'll look at volume by slicing for a cone. So this is a little bit poorly drawn, but imagine this is what we call a right circular cone. So that point should be exactly in the middle there. And I'm going to assume that I have height 10 and base radius 5. And the same instructions here. Let's use slicing to find the volume of this cone. If I choose to continue again using horizontal slices, then we want to first of all think about what those slices would look like, at least approximately. So if I were to slice here, again, we would cut it with a little bit of thickness. And you should notice that, again, we're getting a very similar shape here. In all of the examples that we've looked at so far, you can see there's a circular kind of base involved, and that's affecting that we're getting these circular type shapes. Put this here. And just like we saw with the hemisphere, we're going to find that we can approximate this almost cylinder with a cylinder. It's an almost cylinder because the circle on the top of this green shape is smaller than the circle on the bottom. This height from the base would be HK. This one would be HK minus 1. Here, delta H is going to be the total height of 10 divided by the number of slices n. H sub k is going to be 0 plus k delta H. Again, I'm assuming that this this cone can be placed on the ground. And so we get 10k over n. And then I want to think about v sub k. So kind of building off of the intuition I've gained now from looking at the hemisphere, I see I'm going to get slices that are, once again, approximately cylinders. And then they'll approximately have pi times the radius squared delta H. We get to choose that radius. And again, if I were to just choose the HK, so like a right-hand sum, then the corresponding radius would be the R sub k. So we'd have this. So this part is so far following very closely the structure that we saw with the hemisphere. But of course, this isn't a hemisphere, so there's got to be something that changes. And that comes in this next part. Just like we saw in the hemisphere example, notice that there's a relationship here between h sub k and the corresponding radius. The radius of this top green circle is smaller than the radius of the bottom. So as hk gets larger, I should expect the radius to get smaller. And that means that the volume of each slice is certainly not constant. Again, that makes sense when we look at the picture. And that means that we need to figure out a way to replace RK with its relationship to HK. I don't want to write my integral and end up needing to integrate R against H and not have an idea of how R is dependent on H. So same strategy we saw before. What I want to do is look at this from the front and as a two-dimensional picture. So let me jump to that. Oops, that's not what I meant to do. There. So if I did that, that's what we would get. And again, I've highlighted here where on that two-dimensional picture our slices. So when we looked at the hemisphere, what we got out of that was we used the Pythagorean theorem. Now, notice that's not really going to help me here. If I try to connect this dotted baseline here with this edge, I don't know what that value is. There's not some significant significance to there's no significance to that line I might draw. So let's try to look what we do know from this. There again, I see some right angles, and in particular, notice that this is a right angle, and so is this. So what I can start to take advantage of is the knowledge that I have two similar triangles. So let's try to, so this triangle here, the pink one, is similar to this blue one here. So let's think about why that's significant. For similar triangles, we can take advantage of side ratios being equal. So for the big triangle, we know that the height of the pink triangle is 10 and the base length is 5. Just remember that was given in the problem. So that should equal the height of the blue triangle divided by the base of the blue triangle. Now the base is r sub k. You can see that very clearly. Now we have to be a little bit careful about the height. Notice that the height is not h sub k. H sub k is this length. So if I want to get the blue length here, I can take the full height 10 and subtract h sub k. So again, what I'm saying is this part is 10 minus h sub k. So this, just to be clear, that's what I'm using here. This is useful because what I want to do is replace r sub k in my formula. So you can cross here that this means that r sub k times 10 over 5, which is 2, is equal to 10 minus h sub k. And therefore r sub k is 10 minus h sub k over 2, or 5 minus hk over 2. So what we can do then is go back to our volume of the kth slice. We said that was approximately pi times r sub k squared delta h, which is now roughly pi times 5 minus hk over 2 quantity squared delta h. If I want to then approximate the volume, I can do so by adding from k equals 1 to n the approximate volume of my v sub k. Again, by constructing this Riemann sum, which is a right-hand sum, I benefit because now I can see the structure of what is entailed, and it helps me to construct the appropriate integral. Then again, sending n to infinity, it no longer matters that I happen to choose a right-hand sum, and it becomes exact that the volume here is equal to the integral of pi times 5 minus h over 2 quantity squared dh. And to find the suitable bounds on h, we come back up here and notice that we're placing this cone on the ground. Smallest value of h is 0, and the largest value when I'm at the very top is going to be 10, the height of the cone. So my bounds on my integral are 0 to 10. So when we get here, this is again the setup that I have, and going through this process, now we can say that this is the integral from 0 to 10 of pi. So if we square this out, I'm going to get 25 minus 5 halves h minus 5 halves h. So minus 5h plus h squared over 4. And then we're going to have, let's see, antiderivative is going to be 25h minus 5h squared over 2 plus h cubed over 12. We're going to evaluate that from 0 to 10. So this is going to be 250, and this is going to be, let's see, 5 times 100 over 2, so 250. So those are going to cancel. And we're going to get 1,000 over 12. And 1,000 divided by 4 is going to be 250, so we get 250 pi over 3. So there we get our volume, having constructed an integral. And like I said here, it's very difficult to see that the integral we'll get is what we have here. To get to that part, we really had to take advantage of the slicing so that we could get an idea of what that integrand will end up being.